All right, you ready for the new stuff? This is where the video starts, because we don't need to go over the homework in the video. Here's where we're starting. We're starting with this PowerPoint right here, or this, I'm sorry, this Excel right here. At the top, we used it last week because last week we learned, let me scroll down, NORMDIST, or NORM.dist. But here's today, NORMSDIST. I want to do it a different way. Equals NORM.S.dist. This is the same thing. You can draw the dots on each side, yes, or not leave the dots off. It means the same exact thing. Doesn't matter. I usually leave the dots off, but it doesn't matter. You can do whatever you want. It will work. The only number that goes between those parentheses is when you manually calculated z like you did on the homework. Now, instead of looking on the z chart, you enter it into this equation. All right, so for example, let's go to the homework. Where's our homework here? Is this it? Is this it? Is this it? This is it, right here. All right, so let's go to a manual one up here. Right here. Here it is. We calculated a z of negative 0.58, then we went to the z chart. From now on, you're going to put the Excel equation. You're not going to the z chart. Z chart's gone. Instead, once you calculate that negative 0.58, you then write an Excel equation just like this. You put negative 0.58. There it is. And let Excel. What's our answer down here? 0.2820 is our Excel answer. Now watch what our answer is using Excel here. Equals, what is it, norm? Okay, norm, S-D-I-S-T, parentheses, negative 0.58. Look at it, I'm leaving the 0 off, 0.58. Doesn't matter, Excel will correct it for me. There it is. This should be, what was the previous answer? Hang on, I gotta look again. Oh, I'm moving everything. Hang on. Our answer on our homework was 0.2820. The answer on this, 0.28. What? What was our answer at the top? Hang on, I'm sorry, from the Z chart. 0.2810, and we got 0.2810, because it's getting it off the Z chart, because we're putting the Z in, 0.28095, which would be the same as 0.2810. It's grabbing the number off the Z chart. Don't be wrong. Putting the formula using Excel, like NORMDIST, gets exact answer. Using NORMS distribution replaces looking it up on the Z chart, but it still brings you back the number from the Z chart because you're putting in a rounded Z. Matter of fact, I just realized, we're now going to take it to 4 digits. That's what I just realized. See, for the Z chart, we rounded negative 0.58. Let's not round here. Negative 0.57, what is it, 69? 69. We're going 4 digits, 4 digits. Now let's go back here, let's switch it to 4 digits. So instead of 58, it's 5769. Let me get rid of that 8. There it is, 0.2820. Now we're right with the answer we had when we used Excel, 0.2820. So we're gonna, now, once we calculate Z, we're not rounding to 2 digits to the right and go to the Z chart. That's out. We're gonna go to 4 digits to the right of the decimal and use NORMS distribution. Your homework for week 5, I want you to see this. Oh, that's not it. Where's the Excel? Oh, that's not it either. It's gonna be on your next homework. Let's do another one real quick. I want to make sure you get this, or you guys tell me what to write. I'm going to leave it so you can't see the answer. Oh no, yeah, you can see the answer right there. Okay, here we go. We're not using a Z chart. We just calculated 14 minus 12 divided by 2.6 equals 0.76923. Help me out. Equals norm S distribution. 4 digits. What was it again?
7692.
0.769. Is that what you said?
Yeah.
2. There you go. That's how you do it. You can put the 0 in front of the point if you want. So what do we have for an answer using Excel now that we went 4 digits? Using Excel, we ended up getting an answer of 0.2290. Is this a 1 minus in front? Oh, almost forgot. 1 minus in front here. right there. This is a more than question. So let me enter it in now so you can see an example of this. Equals 1 minus NORMSDIST, parentheses, 0.7692, 0.7692, parentheses. If this is right, it should be, let me look again, 0.2209. Let's take a look. 0.220887, 0.2209.
So we don't have to round?
You, instead of rounding to 2 digits, because we're not using the table anymore, go 4 digits because we're going to use Excel.
Okay.
Now remember, this is only when you manually calculate Z, we're just replacing using the Z chart. We still have this formula when we're not doing anything manually, which has the X, the mean, the standard deviation, and a 1 on the end. That formula is where we're not doing anything manually. This one's when we calculate Z manually, but we're not looking it up on the Z chart now. We're using this, and then we would put the result next to this. Everybody got it? So that's the big change there. Yes.
It's the 1 minus when it's or more or.
Or more. Just like it was when you're doing these and it's or more, you put the 1 minus. The or more or any or at least, whatever words mean a number or larger, you gotta put that 1 minus in front. For almost all of these Excel formulas, you gotta use that 1 minus in front if it's an or more. All right, let's look at week 5's instructions. Here it is. We have a written assignment this week. We have an Excel assignment. Heads up, that Excel assignment is a majority of the points for this week's assignment. It's a long Excel assignment. There's a certain row in the Excel assignment where most of the points are. That's so crucial. But I'm going to go over it in detail on Thursday. It's using count or count if Excel equation to figure out how many of the data exist up in the data on the spreadsheet. Let me show you what it looks like. I showed you for a second. I'm going to make it smaller so you can see the whole thing. So there's the data right up in here. Here it's asking for the mean. Here it's asking for the largest number. Here it's asking for the smallest. Here you got to find the spread. Here you're going to put each one of your classes. Here, is this it right here? Right here. Row 30 on your spreadsheet is where all the points are. I wouldn't say all. A huge amount of your points for this assignment are in row 30 on the spreadsheet. Using count or count if, telling Excel to go up and look at that data and count how many numbers are between each one of those. See all those question marks right here? These are classes. We're going to learn this all on Thursday. And each one of these classes will be designated by you. And then you're going to write equations that tells Excel. Let's say this first class is from 100 to 200. You're going to write an equation that says, Excel, go look at the data and count how many numbers are between 100 and 200. And boom, it brings it back how many. And then this whole line 30 on Excel, has to add up. That formula right there in that cell where that 0 is I'm circling, that's going to be equal to however many pieces of data are up there. That's your kind of your check and balance to say, if that doesn't equal the number of pieces of data, then one of those equations are probably a mistake. You probably did something wrong. That's kind of helps you. And then to finish this out, you got to do your relative frequency or your percent frequencies down here using Excel formulas, using Excel equations, kind of thing, not formulas, but equations. So there's most of the points of your homework. But this part of your homework is coming from the book. Uh-oh, I usually never assign problems from the book, but this one is from the book. Happens to be pages 40 and 41, and in case some of you don't have the exact edition, maybe you have an old edition, or maybe you didn't get the book at all possibly, and if that's true, I posted a picture of page 40 and 41 with those problems on there just to help out, just in case. So on Canvas, you'll see, pick page 4041, that's a picture of the book, and I'm going to open it right now so you can see what it looks like. What are the problems? Number 1, A and B. Number 2, A only. Number 4, A only. Number 5, A only. So let's look at them. What is it, page 4041? The picture closed. How did that happen? I'll reopen it. Look at all this junk. Let me make it big. Okay, someone help me remember. 1, A and B, is that what it said? Okay, number 1. Oh, let me make it a lot bigger. 50 pro football rookies were rated on a scale from 1 to 5 based on the performance at a training camp, as well as their past performance. A ranking of 1 indicates a poor prospect, whereas a ranking of 5 indicates an excellent prospect. The following frequency distribution is constructed. There's your frequency distribution. A, how many of the rookies received a rating of 4 or better? Show me the work. I mean, it's very obvious how many did a 4 or better, but show me which numbers you're adding together to get that answer. How many got a 4 or better? Then it says, how many of the, this is still part A, how many rookies received a rating of 2 or worse? That's also very easy, but show me which numbers you're using and adding together, and then give me results. Show your work. And then I believe you have to do B also. Let me just make sure before I read this. Number 1, A and B. So let's look at B. B says, construct the relative frequency distribution, and then answer the question, what proportion received a rating of 5? You're creating a relative frequency table showing me the work for each number on that relative frequency table. So there's number 1, A and B. Next, I think, is number 2. Let's make sure. Number 2A. Let's go down here. Here's a table. It says the following frequency distribution shows the counts of sales of men's shirts at an online retailer. Small, medium, large, extra large. A says, construct a relative frequency distribution table. And then answer the question, what proportion of sales were for medium-sized shirts? And you just highlight it or circle the one from your relative frequency table that represents answering that question. You circle it or you can answer it however you want. But I need that table. There's where the points are, showing me the work, how you constructed it. I'm going to review how to make a relative frequency table today and how to make a percent frequency table today, and just for the fun of it, a frequency table. So we are going to review that even though we learned that in week 1. Next is number 4, I think. Let me look. 4A only though?
Yes.
Okay, 5A only. Okay, so let's go 4. Got to go down here. In 2018, the U.S. Census Bureau provides a following frequency distribution of the number of people in thousands who lived below the poverty level. Northeast, Midwest, South, and West. The blanky blank in thousands, so that would be, in Northeast would be 6,373,000, because you got to add 3 zeros to the end. Now, A, construct a relative frequency distribution table. Answer the question, what proportion of people who live below the poverty level live in the Midwest? Then you just circle out your relative frequency table, which proportion answers that. Last is number 5. This one I think most people find the hardest, because you got to reverse this. You got to reverse it. So you're given a relative frequency table. There it is. And instead it's asking you how many, where you got to convert these relative frequencies into frequencies. Here's my big hint on number 5. This first sentence kind of gives away what number you should be using. A recent poll of 3,057 individuals asked, what's the longest vacation you plan to take this summer? The following relative frequency table exists. So there's the key, 3,057 people. Now here are the percentages. A, construct the frequency distribution, so you got to convert all of these into the numbers of frequencies. I'm not giving away how to do it. How many, then answer the question, how many people are going to take 1 week vacation this summer? And then you just got to answer or circle the answer you have for that 1 week, 36% of a certain amount. I hope everybody gets this one. I don't want to give it away because it's almost too easy. But again, the key is 3,057. It's such a key number, it's probably in every calculation almost. How's that? I hate to give it too much information now. Okay, does everybody understand what the written assignment is for this week? You're making page 1, or number 1, number 2, number 4, number 5. You're making like 4 tables, but they're not that long. They're each only like 4 items. So 4 tables you're making, and then you're circling to answer each question that's right after you're making the table. All right, good. We're going along fast. Let's go to chapter 1 PowerPoint. Yeah, we're going back in time, and I want to make sure you understand why I'm going back in time. What we've done up to this point is what I designed. I taught this very different than anyone that I've ever seen it taught, as I taught it what I call a building block method. The things when we did the number line is what I call the building block. When we did the number line, matter of fact, we did variances and standard deviation of regular data, expected value, and standard deviation for weighted data. We did frequency distributions, relative frequency tables, percent frequency tables, the bell curve. That bell curve is such a building block for everything. We have so many normal probabilities in our future, and that everything talked about normal probability is all about that bell curve that we've learned each week so far. Calculating Z using the Z chart, binomial probability, normal probabilities, the empirical rule. These are all the main building blocks that I want to make sure I don't leave anybody behind on, because the stuff that we're going to learn from this point on is using a lot of the stuff that we have learned up to this point. And so things go a little faster now because the point that we're supposed to be at is everybody has the building blocks so far. You've got the foundation now. And now I'm going to build on it maybe a little faster than I did with the foundation, and it gets a little harder and the homework assignments get a little longer. So we're going to start with learning the difference between, by the way, these subjects that we're at here, we're right here, qualitative versus quantitative data, cross-sectional data, time series data, experimental versus observational data collecting, bar graph versus a histogram, what makes those different from each other, a pie chart, a dot plot. Most of this is to help you for the next possible multiple choice questions that are coming out of the next test. So this is kind of the boring stuff. You ready? Qualitative and quantitative. I'm going to put it in my own words. Quantitative data is always numbers, but not every time you're collecting numbers does it mean it's quantitative. But if it is quantitative, it is numbers, because you're collecting words. That's not quantitative. Let me give you an example. Here's the data we collected. We're a hotel manager. We asked some guests to fill out a questionnaire about their experience, and they had looks like 5 choices, I think, all the way from poor to where's excellent? Excellent. So poor, below average, average, above average, and excellent. 5 choices. And here's the data we collected. My question for you is this quantitative data, yes or no? Yes or no?
Yes.
No, because they're words. I like your, I appreciate it.
Words.
Huh?
There's a number of groups.
They're not numbers, they're words.
There's five.
There are, but no. Quantitative data are numbers, and they can't be numbers that are representing words. They got to be just numbers. Like the salad question. Let's get the next 30 customers and weigh their salads. All that data we're collecting, those weights, are all numbers that don't represent any words at all. That's quantitative. That's quantitative. This is an example of qualitative. Now I want to take this to another level. Ready? 1 equals poor, 2 equals below average, ... 5 equals excellent. Okay? Now I'm going to switch all this data to numbers. Below average, okay, that's a 2. Above average, that's a 4. Oh, there's an excellent, that's a 5. Even though now I have numbers, because I converted those to numbers, it's still qualitative data because the numbers represent words. But now, here's another one. Ready? I'm going to collect how many cars pass this door on the street between 12 and 1. And we're going to count those cars. And we're going to do it for 16 random days. Maybe it's a Monday, maybe it's a Sunday, who knows? We're going to 16 days. And look at all the data we collected. There were 3 on that day. There was 10 on that other day. There was 7 on that day. But the data we collected are all just numbers that don't represent words at all. That's quantitative. Quantitative is numbers, data that is numbers, and the numbers don't have meanings of words. But qualitative data can be words or numbers if the numbers represent the words. Here's a perfect example. I'm going to go back here. Where is it? Where is it? Where is it? Oh, back. Come on. Wait. Where is it? 17? Where's 17? Oh, it's back here. There is an example. This would be my best example. What was the example I was thinking of? Oh, okay. We talked about it a few weeks ago. Let's go like this. This one neither, right? Is it EI or IE? Neither. EI or IE? That is correct. Thank you. So I'm gonna call 30 households in this certain community to collect the data, whether they have a cat, a dog, both or neither, as their pets. They have a cat or a dog or both or neither. And I'm just gonna enter into the system after I make the phone call, 1, 2, 3, or 4. Because these numbers represent words, that's qualitative. That's qualitative, even though it's numbers. But if we were just collecting numbers that don't represent words, that's quantitative. Quantitative is always numbers that don't represent words. Okay, we got that, because I can already predict a question that might come up in the future. Is this data quantitative or qualitative? You gotta look at it. You gotta decide, is it quantitative or qualitative from the story? That's what you gotta prepare for. All right, let's go to slide 22. Here's another definition for you. Cross-sectional data. Cross-sectional data, you might as well write down time series data because it's all about you recognizing the difference between these two. You'll be told here's some data, and then a multiple choice, is this cross-sectional or time series? Cross-sectional or time series. So here's the difference. If it's cross-sectional, it will be the same, let me make sure I say this right, the same point in time. All the data is coming from the same point in time, the same moment, let's say, or the same month, or the same day, or the same year, same point in time. The example is, we're collecting building permits issued in June of 2007 in every single county in Ohio. So we're getting, let's say there's 50 different counties, we're getting a hold of each county's records, and we're counting how many building permits were issued in June of 2007. Notice we're only looking at one point in time, June of 2007. We're not looking at any other period. And even though we're collecting data from different places in Ohio, we're always looking at the same point in time, June of 2007. That's called cross-sectional data. That's how you recognize it. My key, how I used to recognize it is represents the same point in time. Time series. The data won't be the same period of time. It will be over different time periods, a series of time periods, hence the name time series. This example is that we're going to collect the number of building permits issued in one county called Lucas for each of the last 36 months. Look at, we're not looking at just June. We're not looking at just May. We're not looking at just April. We're looking at the last 36 months, different periods of time in a series. That's time series data. Very different than cross-sectional, because that's the same period of time. So cross-sectional, same period of time, time series, over a series of different times. They happen to be in a row usually. Yes?
Can you say like, that would be 3 years? That would be like.
Yeah, that's right. You can say 3 years instead of 3 years. Well, but then you would be collecting yearly data. You only collect 3 pieces of data. That's why it's stated in months. You're going to be collecting 36 pieces of data now. But it is 3 years worth of data, yes. But 36
Well, like,
of them.
No, I'm saying, but like if it was 3 years, couldn't it be cross-sectional? Because you're saying 3 years, that's your.
No, it would be specific point in time. If it said how many are issued in just 2018, now that's the same, and you're looking at all these different places for 2018, a whole year, or how many were issued for the 3-year period, but you're looking at a whole bunch of different places, then it's cross-sectional. We're only looking at one place and a whole different times, a bunch of different times from one location. That's what makes it time series. I mean, this could have said the state of Ohio, but still that's one place, last 36 months, you know, it would be time series then. Okay, so we got the difference between those two, we can tell them apart. Now let's go to collecting data. The sources in which we collect data from. Here are the 2 most common ways to collect data when using statistics to collect research. Now, why is this important right now? I want to make sure you guys hear me, because there's a certain percent of you who don't even, some of you realize it already, and a lot of you do not realize it. There's a lot of people I know that went to college and got their bachelor's degree, had no intentions of going on to their master's until they got in their job. Then they get into a management position and they see the opportunity to make a lot more money for different upper management positions, but they have to have a master's to get that. They go back to school and get their master's. And whether you realize it or not, this is going to happen to a few of you in here, because it happens, the odds are in my favor of being correct, because it happens to a lot of people. And they go, you know what, some of you already are planning on going to your master's, getting your graduate degree right after a bachelor's, but I'm saying this is the most common way. You go, you get on the job, you see opportunity, you realize how much more money you can make. I did my master's on the weekends. I was out there working, doing my master's on the weekends. getting it while I was working full time. So I did mine after I already graduated. But here's the deal. Not all, but a majority, like 95% of master's degrees require you to write what's called a thesis at the end. That's the big project at the end called your thesis. A thesis is all about that you figured out how to use statistics to do true research. And you're proving it in this little mini project. I call it mini. Mine was, it was like 79 pages, I think. I mean, but here's the deal. When you're going after a doctorate degree, you're doing this again, but you have to do a full research project, which is hundreds of pages. And then you gotta submit it to try to get it published. That's how you get a doctorate degree, to do research. And tons of our professors who have full doctorates, who are here to do research more than teach, you know who some of them are, like some of them only have like 2 or 3 classes like a semester, a whole year, like 3 classes in a whole year because they're focused on research. We, the university, gets paid money from all kinds of different sources that need research to be done, and so we get grants to pay to have this research done. And that's what you learn how to do when you get to doctorate, and you get introduced to it as when you're going to your master's. And when you're going to your master's, you're supposed to prove that you understand how to apply statistics to data to either prove a concept or not, or you can't prove a concept, one or the other. It's just proving that you know how to apply statistics to data. That's the point of a master's thesis. So when you do one, you have to collect data one of these 2 ways, and most of us who got our master's did what's called observational non-experimental studies. For example, a colleague of mine was getting her master's, and she had a whole bunch of the teaching professors agree, she had a sample size of 50 of us, agree to record our lectures. Then she took the recordings and took them back and listened to all of them. Think of it, there were 50 hours worth had to be listened to. She may have gotten some help. And she's counting how many times in the lecture that whoever the speaker is saying things like either a long pause or what are the things that bother you when someone speaks? I can't think of the other words. Like they would say those little things over and over again. And you know, or something like that. What? Something they say over again. So this person said, I'm going to count them all on there. Then she asked all of us to go online and go through this training on how to get those out of your teaching, out of your speeches, how to not say all the time, how not to have long pauses, how not to say whatever the like or whatever word you're saying all the time. And then we all went through that training, okay? Then, I'm sorry, this is experimental, I forgot. I'm telling you a story on the first one. Then she goes back and has all 50 of us record ourselves again. And then listens to all those tapes and counts again. So here's the deal. You have a bell curve. You ready? And you're taking how many the lecturer said before, these bad things before the training, and then again after. And you have 50 of them. And you're measuring before and after. And if they had very similar amount of awfulness after than they did before, they subtract from each other, they come out at 0. So in an experiment, 0 represents the middle of the bell curve in an experiment. And if there wasn't enough changes taking place, if enough of these teaching professors didn't use those words less after the training, then that person working on their master's didn't prove anything. That training didn't help anybody be better speakers. But if the count was so much lower after going through the training, started counting all the ums and all the likes and all the pauses, and there were more of or less of them after the training, then you subtract how many there were before. Let's say there were 6. Now there's only 1, and the difference is 5. Well, the differences end up going up here. And if it's way up here, there's such a difference, you take before minus after. And if there's such a difference that now they're nowhere close to 0 between them, but it's off the chart in the tail, then that researcher proved that training truly helps people who give speeches be better speakers. You get it? That's how you prove whether training works or not. Now in business, this is used a lot in big companies. When you get to big companies, you get up in management, they do these kind of, hey, as a manager, you're going and asking for $100,000 because you want your staff to be trained. Let's say they're sales staff, and you think this training is going to improve their results on whatever it is they're selling. Well, the upper manager who you're asking for this $100,000 for says, well, hang on, let's make sure this training's going to work. Could you pick 5 of them at random to go through it so we can see if it really works? So whatever, they're keeping track of whatever's going on before the training, and then these salespeople, whatever they're keeping track of, should improve after the training. And there should be a difference in whatever's being counted, whether it be the number of sales, the number of no-shows, whatever it is they're trying to improve on. If there's a major difference and the number of them went down, it proves the training worked. And in business, big businesses where they're spending hundreds of thousands of dollars for training, they do this experiment first to make sure the training works, and then you get the approval for all the rest of the money. They go, okay, you want let's see, that was 10,000, here's another 90,000, get the rest of your staff trained. And that's how you get the approval, by applying the statistics to show, look at how statistically there's far less of, or far more sales, or whatever it is, than there was before the training. That's experimental. Now, I apologize, now I'll go to observational. Observational is usually when you're handing out questionnaires and getting people's opinion about something. And you're trying to determine, if the questionnaires are trying to tell you if there's something specific or not. If the questionnaires are all right in the middle here, then that means they're not really trying to tell you anything. But if the majority of them is way up here, let's say that one excellent, or the way down here poor, and you compare it to where things were average, or wherever you expect it to be, if it's so off the chart, then you know something's happening at that business. For example, if we had this questionnaire and there was a whole bunch of them that said poor, it would be obvious. You gotta remember, this questionnaire may have went to 1,000 people, so we just can't look at it. That's why you apply statistics. This is just a micro example. So in this case, we could look at it and go, oh, there's only what, 2 poor? I only see 2. How many excellents are there? Only 1, I think. Is that right? Only 1 excellent, only 2 poor. So here's the count, by the way. Yeah, 2 poor, 1 excellent. So, does that prove anything? Are we doing a great job, or are we doing an awful job, or are we in the middle? We'd have to maybe graph it out, or we calculate a normal probability based on what we expected. But here's the point. Observational data collecting is using like questionnaires or surveys, and you're basically getting feelings or opinions from humans. And then you're showing you can apply statistics to it to determine if this data is telling you anything or not. That gets you a master's degree. I thought of a fun one. I helped a friend of mine. He was getting his master's, and he came over to my house, and he isn't exactly a numbers person, so he wanted my help a little bit. I have several statistics books at home, so I gave him one. But his case was, he loves sports, and it was basketball players, and it was before a free agent, after free agency. He wanted to do it before or after. He collected a bunch of data on basketball players who were about to be free agent. Free agent means their contract's up with the team they're with. They can go to any team, and the agent for that basketball player tries to get as much money as he can from whatever team's interested in that player. That's called free agent. And the point in his experiment, his introduction was that basketball players play their best when they're in their last season before becoming a free agent. And he was trying to prove if that was true or not. So he collected the same data from the same players after free agency was over with, like the second year with the new team. And sure enough, the data proved that a player gets relaxed, they're with a team, they got a long-term contract, their stats go down, they don't want to get hurt, or whatever the reason may be. But that year, before they go free agency, the stats were completely different. The statistics between the stats before and after were so different that he was able to prove basketball players get a different mindset that last year before they go free agency. And it made sense. So that's an example you can take. If you decide to go on to your master's, you can relate whatever your project is to something you love. Like he loves basketball and knows all the players and looks at the stats. So you can connect it to something you like too. It makes writing the project a lot easier. In my case, I was the business manager for a college while I was getting my master's. And they asked me to do a project to help them, which was, I had to collect data to determine the college was starting to have a problem with collecting owed tuition, like backlog of tuition that students had not paid, that they thought they were getting financial aid and it didn't come through, or their loan didn't come through, or something like that. So the college wanted to investigate whether the college should open up their own collection agency, because when you hand off an account to a collection agency, they get a third and you get 2/3 in the first 30 days or 60 days. Then they get half and you get half after 60 days if they collect. And then after that, they get more and you get less if they collect. It's like almost, it's kind of a weird situation. So the college was looking at having their own collection agency. It would have been named something different. It wouldn't have looked like it was part of the college at all. It was just that the college was getting tired of paying all these fees to this agency because they had thousands of students who owed money. So I looked into that, and my conclusion was, no, the college shouldn't have their own collection agency. So that's how mine ended up. And I was statistically did it. So, all right. So now you know the difference between experimental and observational. Let me get back to that slide so you can see it. Experimental versus observational. If this were on a test, you could be told a little story and then asked, is it experimental or observational data being collected? Let's go over here now. I'm going to slide 9 if you're following along. Here it is, a bar graph. Now I feel confident that you all know what a bar graph looks like. There it is. And I feel confident you can probably interpret a bar graph if I were to ask you a question, for example, which rating out of poor, below average, average, above average, or excellent got the best result, was the most common response from this survey? Above average, right? Okay, what's the least common response from this survey? You get it. You can read a bar graph, right? I want to make sure you can know the difference, though, between a bar graph and a histogram. So I'm going to look at the bar graph and look at how it's set up. Now let me show you a histogram. Hang on, I'm going to go kind of fast. What's the difference? Do you see a difference in the way it looks? Yes.
There's no gap.
No gaps between the bars. A histogram has no gaps. I know this sounds weird. Why would one have gaps and not have gaps? I can't. To this day, I have no idea. But a histogram has no gaps between the bars. What was that on here? 10. And a bar graph has those gaps. There you go. There's the difference. Boy, was that hard. Okay, next, a pie chart. Going to slide 11. The only reason, I know you guys can all make pie charts, but the only reason a pie chart's hard is measuring how much of the pie you got to use. I mean, you just can't eyeball it in a way. You almost got to break this pie up into 360 degrees, and you got to multiply. Well, okay, if this is, let's see, what's one of these here? Poor is 10%, right? There it says poor is 10%. So I'd have to take 360 degrees times 10% and get 36 degrees, and then I have to figure out what 36 degrees is on this circle. You'd have to put 360 numbers, you could go by 10, but they'd have to be evenly around the 360. So it's kind of hard to make a pie chart. I'm not going to ask you to make a pie chart, but I am going to ask you to interpret a pie chart. So my question for you is, what was the most common response according to this pie chart? Above average. Good, you can read this. What's the least common response? Excellent, right? You can read this? Okay, so made that easy for you. Now let's go to dot plot. Okay, the dot plot was used in the old days to find the mode, because you could easily see what's the tallest stack of dots, and that would tell you the mode. So that was the most common reason we used dot plots a long time ago. You're never going to use a dot plot in your life, just so you know, because mode, now we got Excel. This is before Excel. But in this case, if you may be quizzed to read one, and if you do, and this is kind of tricky, but what's the most common number according to the dot plot? What's the mode?
62.
Is that 62 or 61? It's hard to tell, isn't it? But we all agree it's that one right after 60, correct? Yeah, okay. That's how you read it. What is the mode? It's the most tallest one. There's no other one taller than that, is there? No. Okay. Is that it? Is that all we got? We got an in-class assignment? No? Any questions? Don't get up yet. Hang on. You want a life lesson?
Oh, yeah.
Yeah, you sure? Because we got time. Are you sure?
Yeah.
Okay, all right. I got one prepared just in case. All right, you ready? Hang on, turn off. I'm going to turn off the video. You can skip the life lesson. You want to skip the life lesson?
No.
All right. All right. life lesson is for all of you who think you're gonna have jobs in a real business someday.